Good evening, everyone. Welcome to last day 4 of QBronze workshop from QBulgaria and QSlovenia. And thank you all for being a part of this 4-day session. Once again, welcome all to the last day of our 4-day session. Myself, I'm Amrit Chetri. I'm the lead and the instructor of this session. And as this being the last day, I'm thankful to the organizers and QSlovenia and QBulgaria for this great opportunity. We are in the day 4, that is, today is 23rd, an inversion about the mean, Gruber search algorithm, then its implementation. These are the complex topic and some idea about the circuit and its uses been discussed in the last session. Before I do start, I'll quickly check I would like to give the highlights of the last 2 days session, which are useful and used in today's topic, that is on Gruber search algorithm. From the first day about the state, any state can be represented in a linear form by using algebraic representation. That's a psi of any state. Psi can be represented as alpha ket of 0 plus beta ket of 1 or ket 1, where alpha and beta are the complex number. And from multi-qubit system, there we discussed yesterday multi-qubit system and Toffoli gate, which is the CC not gate, that's control not gate, which needs first 2 qubits as a controller and the second qubit as the target, 3 qubits. It needs 3 qubits in the reversible computations. And today, before starting, these are some of the topics which are there in our notebooks. Phase kickback, amplitude amplification, and some of the operators and quantum operators, and then basic understanding about the Gruber search algorithm. Phase kickback, as seen yesterday, is the phenomena where phase of a qubit is transferred to another one in a control and a conditional basis, and which we'll see inside the Gruber's algorithm. And it is used in the Gruber's algorithm to enhance its computations. Now, to take to some of the slides, some of the sections of the notebooks today, the first one is the identity operator, which keeps the state unchanged. There is also the tensor operator. Tensor operator creates the combined state of 2 different states. And the direct sum and mathematical operator that also works in the 2 states and creates the one combined state or the set of the states. Unitary operator is an operator that represents the reversible transformation, and other discussion has been done in the day 1 with some introduction to the basics. One more is a projection operator. It projects the states of the quantum system. And we can see 2 more gates there. One is the phase operators, that's S and T. Phase, the first one is a phase gate, second one is the S gate, and second one is the T gate. One applies pi by 2, and the second applies pi by 4 to the same state, that is state 1. And the second part is the sum operator, not the all, which are there, is the next one is a Pauli operator. We already discussed yesterday. There are 3, X, Y, Z, and X flips the bit, and Y is a combined one, and Z again is a phase flip gate. And next to the Gruber's algorithm, it is designed, this algorithm is primarily to work on the unsorted database. and also to solve the black box search or black box search in any quantum problems. It is used in searching the unstructured data in any classical system as well as in the quantum system. It helps in searching the large scale data such as the social media database, and then also to perform the penetration testing or the classical assessment of some of the encryption algorithm. I've been working in this for testing for quite good number of months, not the year. And yes, it has been used in some of the testing to understand the post-quantum cryptography to see the probability of weakening or some of the brute force attempts along with the source algorithm. And in basic structure, the way it's explained, there are two phases. One is the query phases and another one is the inverse phase. The first one is used to attach the negative to the mark element using phase kickback. And second one is the inverse phase that performs the reflection over the means value calculated. Now we are moving to the actual notebooks here. Before this, a quick revision to the yesterday topic or topics. The first one is on the phase kickback. This is the topic covered yesterday and which are essential to understand in today's notebook. Let's see the last one, the effect of C0 gate. Now this solution, we'll check this solution. Now in this one, initially the down qubit was sent to the state 1, and after that Hadamard gate was applied to both the gates, and then again not operator once this Hadamard gate is applied to both the qubits. And then on doing that, we got the circuit in this structure. And here the probability of getting bit string of 1 1 is 100% because this is the 100 search here. Now next, I think as we are lacking the time, would be starting with the inversion about the mean. Now to start with inversion about the mean, here is one game being discussed. Suppose there is an element of n and some of them is been marked, which is the context being created for the Gruber's search algorithm at the beginning. But instead of discussing that, this is one game here. And at the beginning, each has a value of 1. N elements, some of them are marked, not all. And at the beginning, each has the value of 1. Each iteration of the game has two phases. One is a query and inversion, just to map the working of the Gruber's search algorithm. Now the first task, the game has to be played for the value of n is equal to 8. And we consider that only the fourth element is marked. As per this statement, some are marked, means in this case, the fourth element is marked here. The next task is to visualize the element in the list in the beginning as quoted here. Now in this one, the code is like this. Initially there's a level, which is the blank value here. Then the elements is also blank. For a given range of 8, that means it goes from 0 to 7. And the level is added. For this one, we can see the level display here, 1, 2, 3, 4. And then the elements is also marked in the same way as it is doing the similar computation here. But instead of getting this one, what it is doing, it is getting the value of 1. Just on running it. Now, next is to see two different phases. Now, here, what is being represented? There are the 8 different labels. 0 has been added 1, because of that is being displayed as 1, and then is going up to 8 only, because that is 7 plus 1, 8. And this is a simple representation of the game. It's a very simple way to represent. It's really not giving any great context here, but it is the way we considered here. Now moving to the second part of this one, that is, this gives a more context here. Each iteration has 2 phases, the query phase. In this phase, we assume that each mark element is detected and then the sign is flipped, which is the concept of the kickback to apply in the search algorithm later on. The second one is inversion. In this phase, the value of each element is reflected over the mean of all the values. And at the very beginning, Hadamard gate is used to send all the elements to the superpositions to indicate their states, which is the one of the steps in Gruber's search algorithm. By applying Hadamard gates, if there is n element, all n elements is superimposed to indicate their initial states. The next part is, the first step is to check the inversion phase, and the second part is to apply the query. Here, this is the query phase, and the second phase is the inversion phase. Now, there is no great change here, as we haven't added any code. And here are some of the suggestion is been marked here. Change the sign of the mark element, that is multiply it by 1. So anywhere in this mark element, if it is the 4th element is marked, so can be changed that by the -1. So in that case, by copying this, we consider it has to be marked 4th element. In this one, if the 4th element will be I is equal to 3, if I equal 3, in that case, as given here, the sign of the element part, this one has to be multiplied by, in this one. If it is this is equal to, then it can be multiplied by this. Otherwise, it can be the same the way it is there in the first one, or similar. what really happened here. Oh, these labels. So let me put it the way it is. It's working. L was missing somewhere. Could be because of some reasons. We are going to check without any change now. Fine. So here is the one condition. The condition is if I equal 3, we want to add some conditional changes here. The changes would be the element value has to be flipped with -1 into this value. I think I'm correct here. The way this would be. Otherwise, it has to be the same. Same means no flipping of the other states. Uh, 0 and 8. Anything, any suggestion here? This is element 1 multiplied only by 1. Telling the single object 1. What is happening here? This is the 1. This element is the value, so that's value each one. So here probably we can multiply 1 instead of that -1. Here is the issue. This element and element is being added, which is of 1. It is something like this. Well, it is telling if oh, that's I is missing. Still some error here. The moment it is added 3, it is going here. In this case, probably added twice. So number of element is different there. Yeah. Now you can see for this fourth element, the state has changed. It's being flipped downwards to the negative sign. I think you got this. This fourth is being marked, and this is how the first has been represented here. I think it worked. Oh, what I missed here. Yeah, it's okay. A few trials, but it worked. Now going to the second step, query fetch. So you can do the similar here, the way I present above. The task 2. Task 2 is, once again, let me quickly recap. It started with this n elements, and then in the first one, the goal is to mark the eighth or fourth element, and this is a simple representation. In the second change code, we marked the fourth element by giving this condition to flip in the negative direction. So by this one, we can see it is being flipped and is being marked. Now, second task, writing a query. That was the first one. Here also the query part. Out of the two, it has two parts. One is writing the query function. Second one is writing the inversion function. The first one is takes the list of the element and marks the element. Takes the list of the n elements or n plus 1 elements, and then the list of the mark elements, two different inputs. Changes the sign of the mark elements, then returns the results or the list. Once again, if there is a list L, and then again another list mark LM, it takes two different lists here. And what it does, it changes the list of the marked elements and then returns the second list of the resultant list. In case of the inversion function, it takes the list of the elements, all the elements, and reflects the value of each element over the mean of the all values. Whatever elements are there, it calculates the means of those values and returns the reflection of that one. So here is the solution from the team. This becomes a bit difficult at the beginning, but yeah, afterwards, not that difficult to understand. So the first one is the task 1. Is it task 1? The solution is here. Now we are looking into the second part. In the second part, the query, then the elements, then the mark elements. And then for that condition, it has to be marked with this one. I think I would have written this way, much easier, but I followed slightly different, but still that got the result. Then the inversion function, it takes the elements and then computes the summation to get the average. And then it is calculating the mean total summation by the length of the element, which is the one statistical ratio here. And then again, doing the value using the mean calculated here. So new value is equal to mean minus value, the actual value of the individual item minus mean, and then that is being added and is returning that set of the elements here. Very simple. Now next is plotting that one using this function. So in this function or this quote, the n elements is sending there, and the mark element is being represented here, this 3, and then it is expecting the result, the iteration with this function. Now we can see here a very nice mark element that's being clipped down. Earlier only 1, but in this case we send the 3 different is being assigned 3. So in that case 0 to 3, that's 4 element is been marked in the flip side, negative side. Has been discussed quite nicely, so you must have seen here quite clearly. Repeat the task, n is equal to 16, and the element is marked. So here, instead of the one set of the element, it's one fixed. So in the same one, it's quite simple to understand here. This is the 4th task. Again, the similar definition that performs the query operation and the inversion operation in the same way. And there is a one fixed condition to apply the 11th element. 11th element. This is a standard function definition defined. Now this is the place. This is up to 16. And we are expecting the set of the iterations, the sum of the iterations. And on running it, it gives the one set of, that is the 4th one. We have to check the 3rd one. This one. And this one, the element is in the same way, iteration is same, and the first function is also same, the 2 sets of the function inversion. And let's check the outcome here. And 11th, in the iteration, 11th is been marked, and that's been represented like this. And there are this set of the elements which has to be marked, so we can see the clear representation of all the elements. Yeah, there are different iterations. Because of that, the 11th is also marked here. Now in this one, task 4, the 5th element where n is equal to 16th. To repeat the same task, but instead of the 11th, this is for the 3rd and the 5th element. The function is same. That is fifth element here. The 1st, 2nd, 3rd, 4th, and 5th is been marked. Again, yeah, 5th element is being marked, so that's perfectly fine. So in each of the item, the fifth one is been marked, the first, second, third, fourth, and fifth. First, second, third, fourth, and fifth. So if you repeat the same, there is also going to be the similar result or the outcome here. So next is modifying the game further to take it closer to the Grover search algorithm. In this one, we restrict the game by guaranteeing that the list represents the quantum state. So far, we consider that as a classical representation. Now moving towards the quantum state representation. At the initial, we modified uh, at the very beginning, what are the initial values for the modified game? Means how we can represent the same classical representation in quantum state for the same number 8. So here is the solution. This is the task 7. Now here, the solution list is in the quantum state, a set of the vector at the beginning. In the quantum state, then the length must be 8, a to the power 2, which is the element here. And so a is equal to 1 by 2 root 2. This is the number of the element n is the number of the element here. In general, any list with the n element in this representation, this is a statement to understand here before we proceed further. In general, any list with n elements is 1 by root over n up to root over n, up to the n elements as represented here. For any list that is in the list or a vector of that's a up to 8 times, it's 2, 4, 6, 8 elements at the beginning. If it is a quantum state, then its length, we are interested here to calculate the length. The length will be 1. And 1 is equal to a, the length will be 1, this is the fixed value here. And that's in the relation that will be 8 elements, a square, the number of the number value here, the state value here, minus is equal to 1, so that a is equal to 1 over 2 root 2. And in the general list form, it can be represented if there is n element, 1 by root 2, 1 by root over n in this form, because the element is being represented in this a is equal to 1 over 2 root 2. I think it been clear here. Now next is to iterate the step where n is equal to game for 20 steps. The number of the elements is fixed here 8, but iteration, the number of the iteration of the steps is being increased to 20, so that element in the second position is marked. The condition is quite simple. So similar function, it takes 2 different elements. One is for the mark, another is the total list, and then the inversion function, and then the length of the elements, and then prints the list. Here, until unless it is not called in or not been called in another function, we are not going to see the outcome. So the next one, it is directly over the for loop. It is iterating. Now for every one, the length is 1. That means it has preserved the length of the elements. Or the length of the list is here 1, 1, 1, everywhere it is 1, irrespective of the elements of the list. List has different elements here. We can see different one, but its length is being preserved to 1 in all set of the elements. So now this has satisfied the condition here. Condition which were given in this one. Yeah, we already finished this one. We are into the quantum representation modified game. So in this case, we check the list, the length of each of the item, each one, irrespective of the value of the given sets. The next one is repeat the task 8 for n is equal to 16, where the first 12 element is marked. The same one, just modification to the above one. Instead of the 20 steps, we are going to see repeat the task 8 only. So that means 20 steps only. N is equal to 16. This is the changes. This is the first change. Second one, instead of the second element, 12th element has each marked. So here, that is the solution 9. When you run here, here also we'll see the same condition being maintained. Everywhere the length is 1, and these are the different set of the elements. First as this one, and in some places it is almost same but not the same. These are the iterations. So after 20 iteration or the 20 steps, in each of these steps the length is always 1, and the list of the elements is not always same, they are always different. Some may be repeating as per the condition, but the overall sets is not same here. So this is being maintained here. So what we did is that this is the quantum representation or the quantum representation of the given elements. So this part is being finished. Next is the Gruber-Schwarz algorithm. As discussed at the beginning, it is to search for the unstructured data sets. So here, the further modification of the game, which is the main part of the Gruber-Schwarz algorithm. The modified game means the above game, this game which were modified here, is the main function or the main part of the Gruber-Schwarz algorithm, what we going to see further. And here are the some of the pointers or the points. Suppose we have given the unsorted list, we make a search of a specific element, and that specific search is the mark, whichever is search that is marked as the search element. Again, the Hadamard gate is used to superimpose the state of all n elements. We access by oracle, which is the functions, to query the list. Now, very first thing is the superimpose state, which is created by Hadamard gate. And at the beginning, we are started with the unsorted list. If there are n elements, in the list, then log n qubits, we use the log n qubits. Means to represent n elements, there is a need, or we'll use the log n qubits. Each basis state, that is for a given state, basis state, which is the primary state of the Hilbert space we discussed in the beginning, correspond to the index of the list. If a source element is detected, then the oracle flips the sign of the corresponding amplitude. The main function is this one. The oracle functions, or the function of the oracle, is to flip the sign of the corresponding amplitude. Amplitude is basically to increase the probability of finding a sorted element here, and the sign of the amplitude is modified by the oracle function. But when it is flipped, the element, if the element is detected, then it is flipped. Number of the iteration. This is also crucial. Now, by this time, this has been clear in the groovers. There are two functions, or the two phases. One is the query phase, and another one is the inversion phase. And in the query phase, we'll mark the element. We give the negative sign to the mark element. In the second one, we calculate the reflection over the means of the all the elements that we did, and then also represented in the graphical form. The next is to see the actual representation on quantum states. Quantum representations, it's also been done by putting them, or by calculating the length that preserves always one. Now going further, this is the representation. These are the some of the pointers. At the beginning, watermark gate is applied to each of the qubit that takes that makes their state superimposed. Thus, amplitude of each of them is set to 1 by root over n. Now, next is to see the how many iteration is necessary. When the number of the mark element is less than the unmarked element, this is a conditional value. Amplitude of the mark element is start to increase. Once again, when the number of the mark element is less than the unmarked element, suppose it started with n, and n is and n minus 2 is marked. So in that case, n minus 1 element in the set, which is lesser, in that case, the amplitude of the rest of the element n minus 1 is already being marked. So in that case, n minus 2 onwards element is started increase its amplitude. Thus, for the each of the first peak, the probability of observing the mark element takes the maximum value. This is a bit difficult, but we'll see by examples. Now, next is to see the phases. As discussed, there are two phases. One is the query phase. The amplitude of the marked element changes the sign primarily, or it takes minus. The second one is inversion phase. For each of the amplitude, a new calculated mean, which is calculated like this. The mean is equal to, for any item or the any amplitude x, a minus mean. Mean is the total value divided by the number of the element, is equal to twice of mean minus x. Now we are coming to the task 10. convinces itself for this condition. This is to satisfy the condition as per the inversion phase here. So where mean minus x minus mean is equal to 2 mean minus x. So here minus minus, it has to be calculated as so, okay, here this condition has to be verified where n is equal to summation of I is equal to 1 to the n and xi for any given element that has to be divided by n, the total number of the elements. The second one is also to convince in the same condition as given here for this given set of the vector or the representation. Let A, which is the total set of the elements, convince yourself a to the power 2 is equal to A. This has to be verified, and D dagger is equal to D. D is that D? No, not dagger. DT D to the. I guess it's a little bit. D is equal to anything here. Anything dt is equal to dt. This any operation has to give the same set, just like the which what is called I operator or unitary operator here. Now going further, this is just to convince we are just keeping the condition would always remain valid in going further or in applying further conditions. In general form, let's assume that there is n elements, which can be the 2 to the power n elements. N is equal to total number of element, which is 2 to the power n elements, and both are n. One is the uppercase and the lowercase is the list. And once the element is marked, and one of the element is marked. So here once again, n is equal to the power n elements are there for the simple linear representation. And one of the element in this set is already being marked. Suppose that there is a function f whose domain is in this list, within a given list, the first which follows falls in this one, the first list, and the following property: fx is equal to 0, but here is a one condition. Fx same function gives 1 if it is marked, and fx gives 0 otherwise, means if it is not marked. And this marked is done by the kickback function in the further operation. Gruber's algorithm can be defined in more general form, in such that in making it more general, finds the element x so that satisfies fx is equal to 1. So for any set of the elements in L list L, it finds that fx element whenever it satisfies the condition fx is equal to 1. If it is not, that is for the first statement. So this is a simpler modification. Now going further, we access this list by querying f, which is this function, which we'll call the oracle function. That means oracle identifies if the element is detected, that flips or that marks as the detected elements. In that case, it satisfies this condition. I think the things has become more clear at this point. Normally, worst case, we would have to query f for all possible big values, because the iterations has to be there. It is not always fixed. Whenever it finds this element, in that case, it marks. So in that case, there will be a multiple iteration. And then the amplitude amplification increases the probability of finding those elements. Now, Gruber's algorithm or its application is not only limited to find the source element, or not only limited to find the unsort elements in the unsorted list. It can be used to find the shortest distance for different points. And uh, this problem, or this optimization of this kind of problem, is called traveling salesman problem. So in this scenario, for this example, consider there are A, B, C, D, which are the cities, A, B, C, D, and the distance are given here. And the problem, the question, starting in A, does there any path whose distance is lesser than 900, which visits all the cities exactly once and return to A? What is the meaning by starting from A? If if a person has to travel to B, C, D, and then have to return back to A, in doing that, is there any path that takes the distance, or that makes the distance lesser than 900? So let's try in a manual way. If we say in a simple way, if he travels from A to B, that is 100, and B to D, that is 500, and from D to C, that is 800, and from C to A back, that becomes 1,000. But the question, it has to be lesser than 900. Now, other way would be starting in a diagonal way. A to this is being given 300, but there is two probability to go this and this or this. In that case also, if you see that way, so this is 3, then again going there 700, and then going directly to this one 800, and then above 1,000. So the way the algorithm that finds the technique that finds the shortest distance as this condition, as to satisfy this condition, such kind of the decision making or the optimization problem, here it's called the traveling salesman problem. And the possible routes, such as different, I presented the possible route, and to find the distance which is lesser than 900. Now here, one solution is being given: A, B, C, D, A, then B, then C, this 100 and 100, 200, then A, B, then C, then D, this is only 200, 500, then back, that is 800. So there is a one solution. And finding that, it's quite simple by using Gruber's search algorithm. So one is to find the source element, element in the unsorted list. Second is to find the possible path in the traveling salesman problem. This is to represent the different iteration or the different operations of Gruber's search algorithm in a unit circle. Throughout the computations or the iterations, amplitude of the marked or unmarked element is going to be represented by the unit circle that we learned in the day 2. And here, first to include this, and then draw a 1 qubit circuit, and the initially just the fixed value here. These are the state given here. Then by using this function, which is being defined in this file included here, it represents this u. U is simply this. If we change this, then that will be the label. Is being represented here. Initially, we consider the up one, up state, it's marked, and then down state is marked but negative sign. The way we represented the graph in the very first one, in the classical representation. The next one is to do the same, but for the one set of the calculations. Now here is an example. There are 8 elements with 3 marked elements. In the list of the 8 elements, 3 elements are marked. So this is the one. The first one with the state get of 0, 0, 0. And the second in this way thought, which is highlighted and is been marked. And the fourth is again marked, fifth is not marked, and the seventh is marked. Gruber's search algorithm starts in the of any state, and then in this one we consider the state u for a given system, and then applying the condition as given here. As the tensor product here, it is being tensor for all the states here, and after all computations, we have the vector representation to get the combined state of the unmarked and the marked elements together. Then finally, this is the representation of the 8 elements started here. In this one, we suppose the third, fourth, and seventh element are marked. Now, orthogonality is also being used here. By telling orthogonal to each other, the multiplication of the entries results in 0, which is the condition to be satisfied in orthogonality. The pairwise multiplication of entries results in 0, so that their summation is also 0. So this is the condition to be satisfied when we do the pairwise multiplication or to check the orthogonality of the any two state here. The first one is the ux, another one is the uy here. How we can determine the amplitude of the state ket of 0 and ket of 1 based on the amplitude of the marked and unmarked element. So this is the one conditions or the one questions to solve by calculations. To determine the amplitude of the state ket 1 and ket 0 and ket 1 based on the amplitude of the marked and unmarked element. 2 different conditions are here. Now, initially, the u, which is the 2 different values, ux and uy, is been represented as ket ux and ket uy. And in the vector representation, they have been represented or got the representation in this form. and which is further consider that this is the marked one. The first one is marked. The second one is the mark, and the first one is not marked. So all the elements in the first is marked, and in the first one is unmarked, and the second one is all values are marked here. So where every element of marked and every element of unmarked are the unit vectors and orthogonal to each other. So what is the meaning of that? By multiplying the elements of the marked and all marked, will get the value of 0, and their summation is also 0. Now here is the one vector representation. This is based on the value taken here. Oh, yeah, here. Here, one is the marked, another is marked in the negative direction, but unmarked in the other direction, and here also in the negative direction, which is the representation we generally use the coordinate system, the similar way it is in the unit sphere. Now next is to find the amplitude of the marked and unmarked during the computations. The goal is to find the amplitude of ket 0 and amplitude of ket 1. And in the very first one, we represent it by using orthogonality. And now we can see that has been represented, and it is giving a clear representation that they are in orthogonal state. And here now, taking a bit further, as they are the similar explanation further above on top of the above statement, visualization of Gruber search algorithm is also possible using the similar representation or the similar unit sphere representation. In this section, we'll exhibit the Gruber search algorithm using modified game expand in the inversion. So where we represented the state and also represented the two different operations for the series of the tasks up to 9. There were different tasks, and the 9 different tasks were executed to understand this one inversion about mean and their uses. Now you can think that the function oracle and the inversion this is, yeah, we did the one simple inversion or the multiple inversion functions there, and then now we are going to check further with the oracle function. Oracle function flips the bit if it founds the element or it detects the element. Now here are the first task, executing the Gruber search algorithm for 5 steps where n is equal to 16, which is the first one we use in the 2 or 3 different examples. Now next, to draw the state on the unit circle during the execution to check the same and their conditions. Now the first one is the query, then inversion we use there. The second, creating the state, but instead of writing here, to save the some efforts and time, moving to the solution. So which is the task 1. Once again, this is already being created. This is to query, and this is the inversion. Next section is to draw them in a unit circle. Now we got this one, and these are the some observation over the above representation. The operator oracle is a reflection over the x-axis. This is the x-axis, and all these are the reflection, and that is being drawn over the x-axis. Second one, operator inversion is a reflection over the initial state. It's all about the second. Operator inversion is the reflection over the initial state. So here, initial state, it's 0, and there are different iteration. So it is true that it has been moving the first, second, third, fourth, fifth, up to 5 here, and then it is going over the initial state. The angle of the first state, theta, if the angle of the state first one is theta, then the each steps of Gruber algorithm in the rotation is angle 2 theta. So it's that here it looks twice. Yeah, in Gruber's algorithm is a rotation with the angle twice. Yeah, that's fine. In our task, after the step, the probability of observing the mark element is highest. Is there any probability of getting the marked element in the task 1? That is the question. The solution, as we can verify it from the angles after the third steps, because the probability increases with the number of the steps. The first step, second step, third step, fourth step. This has to be a little bigger, but right now the statement is correct. And now in that case, it's asking here in this task 2, after the first step, is there probability of observing the mark element higher or not? So we can see here, as there are only 5 steps. So after the first one, the probability of mark is higher. So here it is marked, right? The first one is unmarked here. In the x-axis is lining here. With each iteration, the probability is increasing. Oh, yeah, this is angle. If it is theta, then the next one will be 2 theta. That's correct. And the probability is also increasing, as this is the element which is the mark element. And again, it's going further for the next iteration or the next step. So if it found here marked, that is flipped, and that is the function of oracle. Now you all must have understood by looking into this unit representation. Task 3, we have the size of 128, and we are going to iterate the algorithm for 10 steps. So this is the representation in the unit circle. As it is iterating, the angle is here is smaller. And the marked element, again, just like that, the probability with each of the iteration of the steps is getting higher and higher. And the angle is increasing. The first, if it is this theta, then this will be theta plus 2 theta, that will be 2 theta, and so on. And from the first second is the theta, it's a linear, but from it increases every time by its iteration by theta. And the probability increases with the number of the iteration as it is at the as it in the, I think here it's marks at the step 4 as per this representation. Now the next task is for the same one, but is the number of the element is 256. Our number of element is higher here. Now with the number of the elements, the number of the steps, it also increases. Now here, as per this one, after the 11th or 12th iteration, it is going to mark the element. As this representation is just like earlier, but the angle, that angle is being reduced here. And we can see the angle actual value. I just skipped this one in the earlier one to take it here. Now here it is 3.58 and then 10.78, 17.8, and so on. Observation. The good number of iteration for k is equal to, for any number k, there are 12 iteration. We can see this at the top. Yeah, here it is been marked. So that is the good iteration for this one. Now we finish this part. Coming to the number of the iteration. If there is a single marked element in a list of size n, then pi root over n over 4 is the iteration can give the marked element with the high probability, which is based on the one we did few minutes back. If we see here, that is the generalization of that finding. As per this one, we got if the k is equal to 1 for the first step. If k is equal to 1, that's okay. Let's see the k here. Is the length of the marked element. In that case, this is the best one. If it is 1, only one element, k is equal to 1, then case the 12th iteration gives the first marked element here. The element is marked with the in the 12th iteration. So on that basis, this is the generalization of that understanding or that finding. If there is a single marked element, that is k is equal to 1, that is a single one, in a list of size n, then pi root over n by 4 is the iteration can apply there with the high probability. Where k is the marked element, if there is n instead of just the single element, if there are k marked element, the way we have seen there, 1, 2, 3, 4, then the better to iterate for pi root over n by k. K is the number of the marked elements, and then the pi is a fixed value. Here n is the total size. If k is unknown, then we can execute the algorithms for different iteration in one way by giving different value like this for 1, 2, 3 times. There is no fixed time if if k is not known. Now this part being optional, just let's move to the, I'll come back here if there is a need of coming here. Now we are going to the last one, that is the implementation, last part of the Groover search algorithm. With this number of the clear understanding about the different section, it's quite easy to write and then to understand. What I mean to say, by following the notebooks in details, everyone would have the clarity what really going to happen if we start from the beginning with this simple classical representation, then the two different phases, and then the examples, then the inversion functions, also the query functions. Uh, by following them, can answer most of the questions, most of the assignment, also can write the code as needed, your own code. Now here we are coming to the implementation part. This is to understand how Groover search algorithm can be applied. And in one of the understanding we understood, or I explained, it can be applied. One scenario is to search for the unsorted an element in the unsorted list. Second one is to find the optimized solution. One of that one is the traveling salesman problem, to find the shortest distance for any purpose, finding a visiting city, bring maximum going to the maximum schools in a city, and so on. Second one is that. Third one is looking for the set of the encryption keys used in encryption algorithm. And there are others, and it can be used along with the source algorithm for the testing of the PQC, that is post-quantum cryptography. Now here are more into the implementation side. Those are some examples. We'll get it into the more into the mathematical understanding of the Groover search for the implementation. We are suppose starting with n is equal to the power n element to the power n element, where the first one element is marked. The task is to find the marked element. One is marked, but that is not known. We are going to use n qubits because it has 2 to the power n. At the beginning, we apply the Hadamard gates, as I said, to put all the states in the superimpositions to represent the n different elements, so that we can put our state into superimpositions. The amplitude of each of the state at the beginning is been represented here to set to 1 root over n. After that, the iteration should follow the algorithm for several times, as really clear at the beginning, only the one element is marked here. So applying the query, which we already did earlier in the different function, then applying the inverse, basically to get the amplitude of each of the states, and that is over the means of all amplitudes. That has been calculated by creating the sum. Getting more deeper to it, query operation, querying for the doing the query to mark the detected value or element, and that function is called the oracle function. Suppose there is a function as defined here that satisfy the condition given here with the following properties. We already discussed this property earlier. Fx is equal to 1. If x is marked, this condition has to follow, as there are 2 more conditions. And fx is equal to 0 otherwise. And then also the more general, it finds the element x that satisfied fx is equal to 1. Now first task discussion. Consider there is a function as given here, but only 2 qubits. And that satisfies this one. Which element is marked? How many queries should we make to find of the marked element in the worst case, or what are the maximum iteration required to find that one. Now, in this case, two qubits are there, the 0, 0 initially, then probability as per the functions, the probability state, therefore 0, 1, then 1, 0, then the second, the third, fourth one is gate of 1, 1. F is also called oracle or the black box because nothing is known to the system at the beginning. Even F might not be reversible, it can be implemented as a reversible function. That's why it is a kind of the black box. Really, it is not reversible, but can be implemented in a reversible manner by using the following idea. Now, this representation is been given here by using UF functions, unitary functions over the given two values are two different state here, ket of x and ket of y with the same functions give the first is a x, which is the marked state, and then again it performs some operations and the direct sum of y with the function fx, the same functions. That's the, it produces the ket of x, but in the second one, if it is y, then the same function gives the ket of y direct sum fx. This is direct sum, which is the another operator. It is not the what is called the tensor operator. If is a straight plus, that is the a direct sum operator. Here UF is the corresponding quantum operator is defined as follows. This is the conditions of the, this is the linear representation of the representation of this operator here. There's a UF operator. And we also learned in calculation that any operator with the any state can be done by applying the tensor product, which is the or the dot product. Instead of multiply, just a small correction one place, I think it was said that multiply. Instead of that, it's a multiplication, but that's the dot product when applying the tensor product. Somewhere I think I realized. Now, next is a sign flip. And this is done by using the phase kickback. In the rest of the discussion in this one, what we look is how the phase kickback is going to impact the overall working of the oracle functions. The basic idea about the oracle function is to change the state once the element is marked. Next, inside that, that's just changing the or signing the flip by using a sign change. We assume that we are going to use a one quantum circuit implementing one operator UF as given in the condition above, an operator which flips the signs of the amplitude. This is to be clear. It changes the sign of the amplitude of the state corresponding to the marked element X. And that is constructed or that is achieved by using the phase kickback. Now, by assuming Yx get minus is equal to not get minus is equal to, we learned this in one of the sessions, that's the first session, 1 by root 2 get 0 minus get 1, and investigate the effect of operator this one over this state. This what is called representation. This is definitely a one quantum state in a vector representation. Now, by applying this one, UF is the operator, and then the this get X and the get minus, and then we are going to get the final state as calculated in this one. We have the following transformation. This is basically being transformed using that operator. Now proceeding further, when the fx is equal to 1, we see that the phase of -1 is kicked back. This is the key changes here we can observe, or we should apply to the front of the first register. This is based, as this is added to the register. Register is the classical register, but in the calculation here, which is being observed in the calculation or in this circuit. And hence, by preparing the output register in the state of get minus and applying that functions which defined in the beginning, we obtain the flip state. Means by applying these functions, the state has been changed, the state of the amplitude is being changed, and that is registered to the that is marked in the register, as the whole calculation are added to the register. Now, even if we don't know anything about the function, as this is nothing known at the beginning as well as when it's called, it does some actions as expected. That's why it's called the black box. Now, next is the task to implement a query phase. If anything not really clear, what are the two options? One is to ask in the your Discord channel. Another is just follow the instruction I share and discuss now. If not, just go through the this notebook once again. And if that makes sense, that's fine. Otherwise, can ping us on private to the mentors as well as me in the Discord channel private message too. Now the task 2, let's n is equal to 4 and implement the query phase and check the unitary matrix for the query operator. Note that we are interested in the top to left, that is 4 by 4 part of the matrix, since the remaining part are due for one of the ancilla qubit. Now here, okay, first let's see, then I'll explain this ancilla qubit. We imported the quantum.py. Then next is to represent that in the unitary matrix. So here is the solution created to solve the problem given there. Once again, now using the phase kickback to flip the sign of the marked element. Once again, this is very crucial. Getting deeper of the working of the oracle function right now. Use of kickback functions or use of kickback flips the sign of the marked elements. Marked elements are the element detected. Set the output of the qubit in this one by applying the X, that is X get, and the Hadamard gets. Then applying this function, which is the oracle function here. Then set the output of the Q register. This is the quantum register. Both are the quantum register here back. So here is the code representation using Qiskit. The first part is same. Then the 3-qubit system here, 3-qubit system been defined here. And there's a quantum register. There's no classical register here. And the my circuit is being created with this quantum register. Next is creating some operation or performing operation for the ancilla. My circuit, then X and H get in this for the same qubit, that is second qubit, the last qubit, third qubit, and then the function UF, then my circuit, and then giving this quantum register. Instead of the circuit, it is taking the quantum register. Again, sending back that one as given above. Then set the output back to this one. First is set the output qubit to this, then applying the X and H, then applying the operator F. By knowing these steps, next just to implement in the code. First is applying the ancilla, that is the first part, by using X and H gates here, and then applying the function, but instead of the circuit to the register here. It is taking both. The one is the circuit and then the register here, and then sending back to the ancilla by using the same function, same operator, and the next to represent in this in the unitary circuit or unitary representation. Yesterday we learned two different representation. One is the Ayer representation, another is the unitary representation. Here it is by unitary representation. Let's check its output. In running that or any task, always check the statement given above. So this is the good practice in going through the different notebooks. Simply check this one. Here, if you see at the very beginning, quite clearly given here, set the output qubit for the Q register to this one to get minus by applying the X and H gates. Is quite clearly given here, only how that can be done. Second one is apply operator UF, which is the grade function here. Then again sending back by calling the same operators. So we did the same here. The first one is sending to the get minus state, and the second one is again calling back. Now here you say that UF is not defined. That must come from this file. And it's being represented in the unitary representation. Now the next task, then also the circuit. You can see here, we'll change the order here. Somewhere, is there any order? Okay, order can be changed, but it's okay, fine. The qubit 3, then qubit, this is 3010 is coming like this because I think when it is defined, it's being added here. Or we can give the value here. You can see the third qubit, we apply the to the same operator twice, first to send to the get minus state, and then again perform one more operation, the functions here. That functions were called in from the file, and then again in the same, but in the reverse order. If we see that one, first here, this is X, but here instead of that one, this is H. That's good. As it's calling to the same, the effect is different. You might be thinking the effect will be same, but no, this effect will be different here as it is to the same qubit. If it is different qubit, in that case, the order doesn't matter, but it is to the same qubit. So in that case, order matters here. And the next one, the task 3. Suppose there is an n elements, an inversion operator is applied next to check whether we can obtain the following matrix or not. The similar one we used earlier is a combination of the unitary oracle functions and then the initial inversion functions. Let's check here by applying this one. Is giving exactly the same output as we were supposed to check that one. Whether we'll get this representation matrix or not, the same matrix is being displayed here. So in that case, the condition is satisfied. The given test scenario is correct. Now next is to test the operation and run the Gruber search algorithm. Suppose we consider there are 4 elements in the list and try to find the marked elements. So far we understood the different steps. Next, to find and apply them. You are given an operator UF been discussed. First run the following cells to load and then access via this register. Is a implementation in the code path. UF function which is defined in the included file, this one. And register qubit 2 is the ancilla qubit is being shared by the query and inversion operators. Now let's get its output. This is to check for the 4 elements in the list and to find the marked elements. There's nothing said about which element is marked here. Now we can see bit string 11, bit string 11 is being observed exactly 100%. Yeah, 100% for the total number of the sorts. I thought that reference 0. And next task is optional but challenging. Implementing the similar function, that is inversion operator, for any number n is equal to 3, where n is equal to 8. This time you need to use the qubits, not 3 but 5 qubits. And need 5 qubits, 3 for operations, 1 for ancilla, and 1 more qubit to implement NOT gate. We understood that for each of the operation in the CC NOT gate, which is the Pauli gate, 1 is required, 3 required, 2 is for the control gate, and 1 for the NOT gate. Same concept here. For this one, 5 qubits, 3 for the operations, 1 for ancilla, and then 1 for NOT gate. And here is the implementation been done in the code. For inversion, that is the operation, it is taking at the range. And on writing this, we'll get the this representation, the function is being called here. So let's work through the code. This is the import part, and then the register, that is 5 qubits, and then creating the circuit with that register, that's quantum register. First is setting to the ancilla to send the state get minus, and second one is the inversion. Big inversion is being defined here above. There's a function, and it uses, I think, some call to the really not calling anything, is a simple for the given one or given conditions as mentioned above. And the next part is sending back to the given operations, as that is a reversible one, and then representing that as the unitary through the unitary matrix by using the unitary simulator here. One more, there's a sixth one, that is testing the Gruber search for the 8 elements using the similar one, and here we can see the outcome. The circuit is getting more deeper and more complicated. By looking into this one, we can identify these are the different operations performed once the different ancilla operation is being performed, the set of this H and X, and then while doing sending back, that is the reverse order here. I think with this, we finished all the notebooks, and let's go further. Yeah. Now coming to the next is the task 7 is done. Now next is designing the Oracle function. Oracle functions, depending upon the problem the statement should solve, we can model in many different ways. And that can be used for the graph coloring, many different problems. I mean, this Oracle function can solve as a model to the many problems. One is the graph coloring, another is the traveling salesman, and many more as a source solution. In solving that, element in the source space corresponds to the quantum states. That is the main working. That's why it is much faster. Instead of searching the whole space, you may design the function f so that it checks whether the element in the search space is actual solution and marks for the outputting or output of 1. And that's already being done. Nothing to write in this statement, just to give the function we created earlier. And here, a further understanding about the Oracle function. What it takes the circuit as well as the quantum registers. This is required to flip the state whenever the element is marked. Now, next is what are the different operations it uses. It uses CCX gate. There's a control NOT gate. And in doing that, it uses 2 qubit here, the qubit 0 and qubit 1. There's a first and second. And the target qubit is the last qubit, that is qubit Q0. Here, Q0 and Q1 are the input bits, and then the QREC2 is the output one. Let's check the matrix corresponding to the query phase. This have been given here. I just want to follow exactly over the notebook. So that's why going through the proper flow of the notebook, just to ensure that you'll also follow this similar one at the first reading. And then after that can refer some of the online resources too. So here we have this similar set of the course, the quantum register, and then the one quantum circuit. Then Ancilla to set to get minus, and then the oracle function. This is the oracle function. So far, few above, the inversion and other. Now generalizing that as a oracle function. This oracle 1 can be exactly oracle function. The goal and the functions and the need of this one is to marked, and which is done by the CCX not get. And now we can represent that by using draw function of the earlier one. Why it is selling that? Okay. Okay, this is not been initiated. Yeah. Now here also the same. Now this operation is the our oracle operations, and x h in the sequence marks is ancilla operation. Back one is the hx here, and in between there is a one operation which is the oracle operation that flips the state to the mark element. Let's take another example. Now the goal is to see the mark element is get of 0, 1. This is, I think, how it is really telling that this is, but yeah, this is the representation. Now next task is the eighth one, implementing the oracle functions, which marks the element get up 0, 0, and to run the Google search to Google search with oracle you implemented, means to create an oracle function which marks the element in the state of get 0, 0. So let's see how this oracle function should be defined or have been defined, which is the last part of the Gruber search algorithm. This is the eighth one. I think I'll take another 15 minutes to finish. Definition this, and here is the solution. This is the task part. The first one is applying the X gate to the first qubit and the X gate to the second qubit, and then applying the CC0 control gate or the Pauli operator. Yeah, it is a CC control not gate by using the first qubits as the control qubits, and then the last one, that is the third qubit in the target one. And then again, following the same operation, that X to the 0 first qubit, and then the qubit in the second position, that one position, that is qubit 1. Many of the problems in the assignments and others based on this understanding, just follow the sequence here. X to the 2 times X, that's for the first and second qubit. And then this control gate, I explained it very thoroughly. You all must have understood by that understanding. Now next is to implement it or to use it. Yeah, here it is clearly said that 0, 0 being observed the number of the times. If there is even small changes in the oracle function, we can see the effect. Let's see this effect. Now, instead of this one, we realize that this should be H. Now, instead of putting in the reverse order, it puts in the superimposition instead. And in that case, the outcome would be different. Now, you can see this observation has changed. Now, instead of getting the desired outcome, that is 0, 0 for 100%, it is being divided 50-50% because the state is being superimposed, or superposition state has been created by this Hadamard gate. So it has to be X. Now putting this back to the X, it sends back to the initial state that's as a reversible. That is the condition discussed. With that, it gives the 100% result as expected. Now here is a further link as suggested in the notebook. This from the quantum gadgets. Gruber search algorithm for unstructured search problem. Can find some time to read it. There's a NOT gate representation, Toffoli gate. Oh, that's, yeah, Toffoli gate. Just be corrected. Okay. And I said that's Pauli gate. Pauli gate is XYZ. And then it has the functions defined here. It's more details about the discussion we had. I think many of them are based on this one or the similar concept. That's why this is a good one to go through it. Second one, it's about the same one, but more into the implementation part. Somehow this site is down right now. When I looked into earlier, more into the implementation and the application of the Gruber search algorithm. With this, I finished my last day's talk. Now I have only 2 words. Thank you all for being part of this session. All the participants, submit your homework assignment on times before the deadline. And if any one of you haven't accepted the invitation to the Canvas, just do that. And once that is done, can submit your homework there. And go through the notebooks at least once before attempting any quiz or the homework. And you can also follow the recorded video given in the links, which are already in the Discord channel. And don't hesitate to send back the queries or ask the queries to the mentors. With this, once again, at the end, thank you all participants as well as organizers for creating this great workshop and inviting me as one of the, I think, instructor and the lead of the 4-day session. A special thank to Mariana for, I think, invitation, opportunity, and being so supportive during this 4-day session.
Thank you very much, Dr. Chetri, for your great performance and for guiding all the workshop as an instructor. Also, I would like to thank all our participants, to our mentors, of course, and to the other organizers from QSlovenia for the great presentations that we had from all the lectures from the quantum computer that we have seen from QSlovenia. Thank you very much, and I hope that soon we'll have the possibility to participate together in additional activities and to make much more interesting things to people in the year of quantum science and technologies 2025, to have them more and more and to be together. Have
Yeah.
a great day.
Thank
Yeah.
you,
I'll
Mariana.
see you. Bye bye.
Bye bye. Thank you.
Bye bye.